All right, let's get started. Today is going to be talking about statistical distributions, but first to address some questions regarding NumPy. So NumPy does come up quite a bunch in the lessons here, just to like make certain counting things a little easier. The first question I had from Ali was about random seed. Random seed is actually something that we are going to be using for actually throughout this phase and next phase as well. So random seed, you might see it as an argument to some of the NumPy functions. Anytime you see random seed or a seed equals to something, it basically keeps you at a consistent random. So you can imagine that, let's say, in one of our, maybe as an exercise, you want to code something that draws like 5 numbers out of the range of 1 to 1,000. Having a random seed means that if someone was to rerun your notebook, you would draw the same 5 every time. So in random seed, you usually feed it like any integer. And then with a different integer, you have like a different consistent random. And so how random seed works is if you, for example, you're writing a notebook and you like randomize some part of it, but you want someone to be able to replicate what you're doing, all you would have to do is give pretty much every random function that NumPy has, you can feed it a seed, give it any integer of your choosing, and just keep that constant. And the random that occurs in your notebook will be replicated for the purpose of, what's the word that you can like just do the same thing over? Reproducibility. That's the word. So yeah, you will come across random seed in the next couple of phases, and we will see it, I think, in pretty much every topic is going to pop up here and there. Any clarification on random seed?
The bigger the integer number is, it's harder to predict?
Not at all. It actually doesn't matter what the integer number is. It's just like it sets the random. Basically, like if you set random seed equals to 1, it is, if you're pulling like 5 numbers out of 1,000, it'll select like a certain set of 5 each time you rerun the cell. But if you set random seed equals to 1,000, which you can feed it any integer, it'll just be a different set of 5 each time.
Okay, thank you.
Mm-hmm. Oh, I see a comment saying that random seed sets the first random item to always be the same, which guarantees that the rest of the randomization is replicated. I'm not too sure, honestly, about like whether it sets the first thing to be the same, but yes, it does guarantee that all the randomization is replicated. You might see that in some, I'm not sure if it is actually in some of the lessons, but it's possible to actually set a random seed for your entire notebook. And then that just means that you don't have to feed it specific seeds for each random thing that's going on. But yeah, in terms of like the intricacies of how it's working exactly, I actually don't really know. But what I know is if you set a random seed, it just means that every time it is going to still be random, but it will be the same random every time. And that's sometimes useful, especially if you want to like test different things on a random specific set of things, which will make more sense when we get towards the end of the phase. Hopefully that makes sense. The next thing Melody asked was about NumPy Any and All. So Any and All, I actually agree is kind of tricky to understand, but I have the specific example. I just did like a control find to see if it's this one. Yeah. So it was brought up in this question of, it's brought up in this question of the let's see, outcomes when throwing a dice twice, and you just want to find the ones that have, I think, a 5 in them. So how the any function works is this array has all of the pairs of possibilities of your dice throws. That's the setup of this. It's a 2-dimensional array because of this. It's 36 sets of 2s. and how numpy.any works. And when you look for, something to have a 5, and this is the condition that you give here. In numpy.any, you can give it a condition to look for, and then this axis equals to 1 means that it's looking at each pair. I believe it's if you're doing axis equals to 0, it'll check all of the first dice throws and then all of the second dice throws. But in this case, they're looking at each pair, whether there is a 5. So that's what the axis is. If you were to have a greater dimension in NumPy array, you would be able to do axis like 2, 3, so on and so forth. But very unlikely that we will be faced with that situation. But how the .any works is it's actually masking this condition over this array. So to see if, all right, are there 5s in here? They're going to go through each pair and take a look and see if there are any 5s. So here you can see this is the result of that, where you have the first 4 are false because there are no 5s in the first four pairs, and then true for this 5th one. The difference between any and all is that I believe all will look for whether both are 5s. So I think if you were to, instead of doing .any, do .all, there will only be one true element. Does that explain it? To be very honest, whenever I'm using .any or .all, it is a little bit of a trial and error to like figure out like which axis we're testing against. But that's like, I guess, my quick explanation of how that works. I don't know if that was helpful or not.
It just basically sounds like you do the same thing that I did. I'm like, well, if I put axis equals 0, it gives me a pair. If I put axis equal 1, it gives me, a line of items.
Yeah.
I just had to switch back and forth.
Yeah, exactly. I think I also do the same thing. I always honestly don't really remember. I personally don't remember, like, I think when it's presented as like pairs rather than like a table, I always get confused in terms of like what the axes are. So I think that's fine. You're really only switching between 0 and 1, and if that's like what you wanted to clarify. Really quickly, I just saw the question that Sarah had. Okay. I see this question. I wasn't going to talk about this specific question, but I'm going to add it to the list of questions that I will discuss next week, just because I want us to be in like a probability frame of mind when we go through probability. But okay. I have this saved now, and I will put that in the list of questions. And yeah, I'm still finding the best time to do this, but it'll probably be early next week. Cool. Any other questions before we dive into topic 12? Cool. All right. So topic 12, let me just arrange my windows a little bit. There we go. So topic 12 is on statistical distributions. Really quickly, the stuff that we're going to cover, we're going to talk about expected value and variance. Expected value is this E of X, variance bar of X. Some definitions here of PMF, PDF, and CDF, which I'll go through later. Bernoulli and binomial distributions, we're going to talk about extremely briefly because the session that I'm going to talk about probability questions, I actually want to bring this up as well during that time. So I'm going to explain that more in depth next week because it's a completely different distribution from what I think is the main point of this topic. Normal distributions, which is the main point of this topic, and then quickly talk about what a one sample z-test is. With this topic, I do think that like the specific things are a little all over the place, but the main focus is going to be understanding these graphs, these PMF, PDF, and CDF graphs, and what they mean and what information you can get from them, as well as what a normal distribution is and a little bit about z-testing. Our upcoming study groups go a little bit more in depth into testing, but I think there's an example in this slide deck that will sort of like set the stage for that. But in terms of like expectations for this topic, any questions? All right, let's see. All right, so first of all, expected value and variance. So first, to start with expected value, here I have some formulas, but I'm going to explain them in a little bit. If you have a random variable, and a random variable is basically like something that has a range of possible outcomes. So rolling a dice is actually also considered a random variable. Flipping a coin is a random variable as well. For every random variable, you can calculate an expected value and a variance. For a dice roll, if you were to roll a bunch of times and expected value, this mathematical notation looks a little bit intimidating, but it's basically what is your average overall value. And for a dice roll, you're sort of thinking, all right, if I have, 1, 2, 3, 4, 5, 6, each of them having a roughly equal outcome, your average value would actually come out to 3.5. And that's because, you take 1, 2, 3, 4, 5, 6, add them together and divide it by 6 because, they all have an equal likeliness of being thrown. And so with that, we can sort of break down this equation, which I know looks a little bit intimidating for anyone who hasn't seen mathematical notation before. But to break it down, each x sub I, so this in the math world is known as x sub I, sub because the I is subscript. So each x sub I represents an outcome. So in a dice roll, x sub I can be 1, 2, 3, 4, 5, or 6. And whenever you see something with a P that's wrapping around something, so basically this part, which I'm gonna just circle really quick for clarity, this part here is the probability of x sub I. So those are the two parts here. This dot is the product of. It gets a little confusing because sometimes, the time sign is also an x, but then we use x for variable. So sometimes we use a dot to mean multiplication as well. So what we're doing in this formula, we're taking the probability of an outcome multiplied by the outcome itself, and then we're summing it all together. So in the context of a dice roll, we have 1, 2, 3, 4, 5, and 6. So actually, let me just roughly draw this somewhere. So with a dice roll, let me do it over here. Actually, we have 1, 2, 3, 4, 5, and 6. And then we have the probabilities of each of them. And the probabilities of each of them are 1/6 each, right? And then same for these. They're all 1/6. How we evaluate the expected value of the dice roll is we're just taking 1 times 1 out of 6 plus 2 times 1 out of 6 plus 3 times 1 out of 6, so on and so forth. So here we actually get 1 out of 6 plus 2 out of 6. And here I'm actually multiplying the first row by the second row, multiplying it, 3 out of 6, so on and so forth. And then this will actually sum up to 3.5, which is the average or expected value of all your dice rolls. This mathematical notation can be a little bit confusing to figure out. Basically, whenever you see this like funky E, it means you're gonna sum things up. And if you don't see any like bigger brackets around specific things, it's safe to assume that you are first gonna do this inside part and then sum it together. As we come across more of these like formulas, I'll try and break things down, but please like feel free to interrupt and like ask clarifying questions if needed. So that's expected value. If we have like a coin flip, and let's just say, just for like numerical purposes, we'll say 1 is heads and 0 is tails. Exactly the same process. Heads has a 50% chance of showing, tails 50%. So in a similar way, if we do this calculation, the expected value of a coin toss is 0.5. Now let's say you have like a weighted coin where you have like a 80% chance of getting heads, but 20% chance of getting tails. That's when it's a little different. I mean, using the formula, it's the same, but because of that, because all the probabilities are not equal, so let's say for a coin toss, we have the possibilities of 0 and 1, whereas 0, you have a 0.2 chance, and a heads, you get a 0.8 chance. If we were to do that multiplication out, this becomes 0, this becomes 0.8. And if we were to add these together, your expected value becomes 0.8. So that's what expected value is. This formula definitely looks a little scary, but it's really just multiplying the value itself with the probability and then summing it together to sort of get an average. And if you have different probabilities for different things, you sort of have like a more weighted average that is more that's more indicative of your overall average. Questions about that? All right, well, good news is there's NumPy built-in formulas to calculate expected values for you. So you don't ever have to do the calculation by hand. Although I do think some of the lessons do have you do that. All right, the next thing I wanted to talk about was variance. And variance is basically how spread out your data is or how different the possibilities are. So for variance, the formula looks kind of similar, but is a little bit different. So because variance is actually measuring how far away from the average value on average your outcomes are. So just say again, the variance is measuring on average how far away from the expected value your possibilities are. So in other words, just saying like how spread out your outcomes can be. And the formula, the first part of the formula is kind of the same. You're looking at the probabilities here, but instead of looking at just the value itself, we're also looking, instead of doing that, we are looking at the deviation from the expected value. Because that is sort of a measure of like how far away from the expected value of an outcome is. We're doing that, and we are also taking the square root, sorry, not square root, we're taking the square of it, because if we had positive and negative values, sometimes they just cancel each other out, and just to maintain a count of if you're deviating from the average in different directions, you're taking the square of that, because when you square a negative number, it becomes positive. Questions about that? Again, there are also built-in methods to calculate variance, so I wouldn't worry too much about that. So this is the very general formulas for expected value and variance. For other distributions, and we'll see that in the normal distribution, we'll see that with like the binomial distribution as well. There are often formulas that simplify this for expected value and variance. So you don't have to do this exact calculation every single time. Questions about this so far? These are just more like definitions to be aware of. Not so much definitions, or at least just know what the expected value is telling you and know what the variance is telling you. All right, to continue, we're going to start talking about the PMF, PDF, and then CDF. And I'm going to like outline the differences after going through all three. So the probability mass function actually associates probabilities with discrete random variables. So discrete random variables are basically things that have a known number of possible outcomes. So most of the examples I've been giving out, like dice rolls, coin tosses, those are all discrete random variables because you know what the outcomes are. The outcomes can be represented as like a set of like numbers or outcomes. And what a probability mass function shows you, and very often it's either given to you as a formula or as a graph like this, or in some way that you can turn into a graph like this. It basically shows you for every outcome, what is the associated probability. So here, I guess this is, I don't know, we can assume this is some sort of 5-sided dice. And in this 5-sided die, for like the outcomes 1 and 2, the probability of getting that is going to be like roughly like 0.31. So like 31%. That's basically what a PMF is showing you. Probability mass function just shows you the probability distributions across the outcomes of your discrete random variable. Sound good? Does that need clarification? So yeah, in the case of this, I guess 5-sided die, there's a 15% chance of rolling a 3, looks like an 8% chance of rolling a 4, 15% chance of rolling a 5. And this is what the PMF tells you. If you have, something that has like more outcomes, like a weirdly weighted 20-sided die, for example, this bar graph can look more complicated. But your probability axioms still hold in that everything's going to sum up to 1, and you won't have any negative probabilities as well. Any questions? All right, so that's a probability mass function. I actually personally confuse myself all the time with this next one as well, because this next one is called a probability density function. The probability density function is literally showing you the same information as a probability mass function. The difference being that instead of a discrete random variable, probability density function shows you the probabilities with a continuous random variable. So I don't think I've mentioned any continuous random variables yet, but basically to contrast with discrete probabilities where, you with a dice roll, you can only get 1, 2, 3, 4, 5, and 6. Let's say you have a variable, like in this case, I think it's temperatures on a specific day in New York. Your temperature has all of these ranges. You can get as granular, as many decimal points as you want, and therefore there are kind of like infinite number of outcomes, but you can sort of graph the probabilities of these outcomes in this continuous line graph. So that's the difference. Here you can sort of see with this, if this bar can be moved, but it can't. But anyways, for example, here the temperatures are down here on the x-axis. So let's say, all right, what's the probability that you have temperature of 75 degrees? And so that would roughly come up to like around 4% chance. Same thing with like, all right, let's say what's the probability that the temperature will be 80 degrees? This would be maybe about 13% chance. So this is really showing you the same thing as the probability mass function, just that this, the term used for a continuous variable is just different. It's just probability density function instead of probability mass function. One thing that is used more for probability density functions, you can actually look at ranges of things. And this is actually where a little bit of calculus comes into play, but you don't have to know the calculus exactly. But let's say you wanted to look at, all right, what is the probability that my temperature will be between 75 and 80 degrees? The way that math works out, and I won't go into like all of that, but the way that math works out is that the probability of your temperature being between 75 and 80 degrees happens to also be the area under the PDF between 75 and 80. And so very similar to like the PMF, the probability mass function, where every bar will sum up to 1. In a probability density function, the entire underside of this curve, also known as the area under the curve, actually sums up to 1 as well. That's just like a neat thing to know that, all probabilities do sum up to 1. And so if we're looking at, all right, what's the probability that the temperature is between 75 and 80? There's built-in code that can help you calculate the area between this, and this would be your probability. So in this example I have here, you can also sort of estimate it with a histogram, but that part's not too important. But just imagine like, all right, we have this same curve here between 79.3 and 80 degrees. And this is this red area here. I think I took this from one of the lessons. This bar happens to be 13% of the area under the curve. That's just another way that you can use a probability density function. Something else to mention is this bell curve shape that we're seeing here is just so happens to be the shape of this probability density function. You'll see in some of your lessons, you can have probability density functions that look like any shape. They can really look like anything. Just that, under the curve, it has to be an area of 1. Questions about that?
I kind of forgot the integral rules.
Yeah.
Do I need to review them for calculating this, or?
No, we don't have to review the integral rules. Yeah, so what Ali's actually talking about is to find this specific area, you actually have to take the integral of this blue function between 75 and 80. That's something that we learned in like statistics and math. But for our purposes, we don't have to talk about integrals. There are built-in PDF and CDF and I'll talk about CDF next, but there are built-in functions to calculate this for us, and we don't have to do that by hand.
I have a quick question. So on the y-axis, you said that, for example, for the temperature to be 75 degrees, the probability is 0.04. Is it the probability? Because on the other graph, it says density for the y-axis.
Yeah, the terms here are interchangeable. Yeah, yeah.
Okay.
So yeah, because theoretically speaking, you don't generally ask about when you have a PDF, because of like the whole like infinity number of decimal points thing. You typically don't ask about a specific point. If you want to get like more granular into the math of it, and if you like do any of like the statistics reading, they will mention that like when you're talking about probability density function, you're always asking about a range, which is why here they're asking about a range. So specifically, we wouldn't ask, all right, what is the probability exactly at 75? Even though it will be very close to this amount, usually you would ask, all right, what about, instead of asking for 75, you would ask for something like between 74.9 to 75.1, and then compute that area. So that's just being a little bit more technical and I guess more correct. But for simplicity's sake, you can sort of
estimate.
Estimate that is the probability. But yeah, that's a really good clarification as well, because
Thank you.
that is a point that does confuse some people in the lessons. But yeah, anything else to clarify about PDFs? All right. Now the third one is CDF, cumulative distribution function. So there are actually different definitions out there, but in our curriculum, cumulative distribution function can refer to the same thing for both discrete and continuous variables. The only difference is sometimes I've seen the term cumulative mass function to refer to discrete and cumulative distribution function for continuous, but CDF works for both in our curriculum. And as the name suggests, it shows you the cumulative probability. And in some cases, this is useful. So this is the CDF of a dice roll, and basically it's cumulative, right? So just to break down this really quickly, because that notation might come back up, this notation over here of P big X smaller than equal to X, you're basically looking at what is the probability of something being under a certain value. To use this dice roll as an example, let's say I want to know what is the probability of getting a dice roll that is 4 or under, 4 or below. 4 or below in a PDF, and in a PDF to get 4 or below, there we go. In a PDF to get 4 or below, we're just going to sum up these 4 bars, right? Because that's the probability of getting 1, 2, 3, and 4. But if we had a CDF, all we would have to do is look up the value at 4. And the value at 4 here is, I think it's going to be roughly 0.66 because this is a 6-sided die, and then, yeah, it steps up. So basically, this is just a different version of, it's really just the PDF, but the blocks stacked up on top of each other as the numbers increase. Same thing for continuous variables. You can sort of think of it as like sort of stacking on top of each other, but it's just cumulative. So if you ever wanted to know the probability of the temperature being below 85, the probability of being below 85 would come up to like about, I don't know, 95%. And instead of having to like, compute an entire area, you can just look up one single value. And with a CDF, sometimes it can also be helpful to do a range, because let's say I wanted to know 75 to 85. 75 to 85, I can just take this value, which is, let's say 95 for now, look up this value, which is, let's go with 5, and then just take that difference. And then by doing that, we have basically found out what this probability between 75 and 85 are. Gotcha? All right. CDF is a little less common, but just good to know that it exists, just in case it comes up in like an interview or anything. But questions about these 3 graphs. Just to note that the ones for cumulative are different from the ones for, the ones for continuous and discrete are just named differently. in these cases. But sometimes when you're asked to calculate probabilities, you might be given like one of these things that you can use to, you know, calculate, for example, expected values, variances, stuff like that. But these are just good phrases to know. All right. Really quickly, we're going to talk about Bernoulli distribution as well as binomial distribution. I'm not going to go very, very in-depth into it because I will be like having like a dedicated session for this and the other probability questions next week. But just to know that the Bernoulli distribution refers to any distribution that has a one-trial binary outcome experiment. So for example, a coin toss follows a Bernoulli distribution. If you're like shooting a basketball and you know you just want to see what's the probability of getting it in or not in, that is a Bernoulli distribution. So in this case, we can say that, all right, X, which is, let's say that we want to look at the probability of, you know, shooting a basketball into the basket. It can be modeled with a Bernoulli distribution. And let's say you're like really good at basketball and you get the basketball in like 80% of the time. And so this notation here is just saying that X, which is your random variable of throwing a basketball, follows a Bernoulli distribution with probability 0.8. This notation, we're going to see different versions for different distributions, but for Bernoulli distribution, you just need to know the probability of, you know, your success, which is 0.8. Very similar to what we were talking about before. I think I actually used 0.8 as well. If you were to calculate the expected value and variance, the expected value of a Bernoulli distribution is 0.8. And I think if you were to like do the variance formulas, you would come up with a variance of 0.16. You might think that, okay, what's the point of this Bernoulli distribution? It's pretty simple. It's just like one experiment happening one time, and you have, you know, either success or failure. This actually leads into the binomial distribution, but I think it's important to like set up these definitions first. But any questions on a Bernoulli distribution? Literally anything that has a binary outcome and you only conduct one time is a Bernoulli distribution. All right. Building off of that, we have the binomial distribution. And binomial distribution is very similar to the Bernoulli distribution, but the main difference being that it is multi-trial. So in this case, let's just say that, you know, you are playing a game where, you know, you're going to shoot a basketball 3 times and you want to find like the probability of getting it in once, twice, or 3 times. That is a binomial experiment. And I'll break down the formula next week. But parameters that are important in a binomial experiment are the number of trials. Oops, I thought it was going to be a box. All right. The number of trials and the probability of success. So those are the parameters that you need to know. And this kind of looks very similar to the Bernoulli example, but instead you have to tell it how many trials we're doing and what's the probability of success. And here we're calculating what's the probability of succeeding 0, 1, 2, or 3 times. So this is actually the formula for calculating the exact probability, which I will break down next week. But some things might look familiar. This is actually the combinations formula. This part over here. This is the combinations formula. N choose k is the same as saying like, all right, n factorial over k factorial times n minus k factorial. That's the same thing. And if you were to evaluate these things, you can get the probability of x equals to k. And k has to be 0, 1, 2, or 3 in this example. Does this make sense? And then this, you're just taking the probability of success to the power of the number of times you want to calculate your successes for, probability of not success to the power of basically a number of failure times. And then that's your formula. I'll like break this down more next week. But again, for this, you have expected value and variance for this, which I think the formulas are actually, in this case, n multiplied by p. So it'll be like 3 times 0.8 for expected value. And your variance formula, I'm not even sure why I remember this, but it's n times p multiplied by 1 minus p. And that gives you 0.48 as your variance. And these are what I mean by the formulas that are already defined for specific distributions, such that you don't have to do the, all right, calculate probability of x multiplied by x plus probability of x multiplied by x over and over again. These are just formulas that have already been simplified for this specific distribution. But any questions about this so far? I will definitely get way more in depth into this next week. All right, next thing to talk about, the normal distribution, which is much more important. There's a lot of text here, but not to worry. A lot of this is actually copied over from the labs. But the normal distribution is a whole type of distribution that's very important in statistics. Other words for the normal distribution is a Gaussian distribution, or more, I guess, widely known, a bell curve. So anything that looks like a bell curve like this is a normal distribution. All of this text is specific features of a distribution that you can start calling. Basically, it has to meet these features so that you can call it a normal distribution. So with a normal distribution, they're all symmetric about their mean. So the mean being the center point, they're all symmetric. And by the way, this is the PDF of a normal distribution, by the way. This is a PDF, and so they're symmetric about their mean. In a normal distribution, they have the same mean, median, and mode. If you're testing if a distribution is normal or not, you'll actually calculate their mean, median, and mode and see if they're the same or similar. Like every PDF, the area under this bell curve is going to be equal to 1. They are denser in the center and less dense in the tails, thus the bell curve shape. They are defined by 2 parameters, the mean, or expected value, and the standard deviation. So those are 2 things that define a normal distribution. So you actually can have different normal distributions with different means and different standard deviations, but they all have the same shape, just sometimes like a little fatter, a little taller, depending on the mean and standard deviation. One other thing that's pretty important to remember is for a normal distribution, the proportions of the bell curve are also kind of important in the sense that around 68% of the area of a normal distribution is within 1 standard deviation of the mean. So what that means is that if I were to shade in, and these little sigmas, these sigma signs mean standard deviation. If I were to shade in this area between the first standard deviation, so plus and minus 1 standard deviation, this is 68% of all my data. All of my data is between 1 standard deviation. So if I had a normal distribution of, let's say, mean 20 and standard deviation 4, 68% of my values will be between 16 and 24. Similarly, 95% will be for 2 standard deviations. So if I was to widen it out with my distribution of 20 and 4, I would have 95% of all my values between 12 and 28. And I think it's actually 99 for 3. Yeah, but that's a little less important. So these are all the characteristics of a normal distribution. Question about that? All right. So with the normal distribution, I mentioned that it is defined by expected value and variance. So expected value is actually just straight up the average, the mean of your normal distribution. And variance is the square of your standard deviation. Formulas for the PDF and CDF, you probably never have to use this, but just to know, these are actually the formulas that if you were to, like, I don't know, graph it on a graphic calculator, these are the formulas that you would have to plug in to form these distributions. And this graph is really just to show different normal distributions. So you can see here we have like the first 3, which are the blue one down here, the green one, this tall one in the middle, and this red one, this red flat one. they're all normal distributions, just with slightly different parameters, slightly different standard deviations to be exact for this one. So here you can see that the blue one, I guess, is the most regular one because it has a standard deviation of just 1. It's sort of like in the middle of all of them. If you have a smaller standard deviation, it means that more of your values are clustered around the middle. So that's why, you know, it's taller in the center. And then the red one, where you have a bigger standard deviation of 3, you end up with a much flatter curve. And the reason why, you know, the standard deviation affects the height is because the area still needs to be equals to 1. The area under the curve from negative infinity to positive infinity, no matter like how far the tails go, has to be equal to 1, which is why when you change the standard deviation, the height of the graph also changes. And finally, this is just another one. This yellow one is just with a different mean. So it's shifted based on the mean. But questions about this? This is just to show how different normal distributions can look. All right. So we've talked about how there can be different looking normal distributions, but there's actually something called the standard normal distribution. So out of all the different kinds of normal distributions with like different means and different standard deviations, there's actually a standard normal distribution, and that is a normal distribution that has an expected value of 0 and a variance of 1. Variance of 1, standard deviation of 1, because they're like square and square root of each other. The values are the same. And what's important about the standard normal distribution is if we wanted to compare 2 different normal distributions, what we can actually do is take all of these and sort of convert them all to standard normal distributions so that we can compare them a little better. It's like allowing us to compare apples to apples versus apples to oranges. So imagine if I had, you know, a class that, let's say I want to compare different statistics about, let's see, an example that we're going to talk about later is drug trials. And we can talk about, like, you know, the distribution of, like, I don't know, I think one is like blood pressure between a group of people that have the drug and don't have the drug. And you have like a different number of people in each group, and you have like a different mean and standard deviation. You convert these to a standard normal and compare them more equally. We'll talk about more specific examples later. But basically, you can convert any normal distribution into a standard normal distribution. And there is a formula that I'll talk about, I think, right after this. So for example, if I had this distribution on the left here, which let's wait for that bar to go away, and this distribution over here looks like test scores from 0 to 100. There's a mean of about 50, and I'm not too sure what the standard deviation is, but we can actually convert it to a standard normal distribution such that it becomes centered at 0 and then having a variance of 1. And so we can actually do this process of standardization where we can take the left graph and turn it into the right graph. Something to note is the shape of the graph remains the same. Maybe the scale's a little different, but every point on the left graph has a corresponding point on the right graph. So you can see here, this point here of, let's wait for that to go away. That point there of about 70 with a probability of roughly 0.005. 70 will convert to 2 having the same probability. Gotcha? So this process of turning any normal distribution into a standard normal distribution is known as standardization. And each of these values that are converted from this distribution to this distribution, these values, these new values that you get here, so 2 in this case, is the Z-score of 70 in this distribution. So any number, and I'll show you the formula in a little bit, any number from here that you standardize and convert into this right side graph. So yeah, any number that you take from here, convert to this right side graph will be the Z-score of the number in the left side graph. I hope I didn't lose too many of you there. All right. So formula to do that is down here. So just to explain what a Z-score is used for, there's a lot of text here, but a Z-score basically tells us how many standard deviations away from the mean a point would be in a standard normal distribution. So the z-score is associated with cumulative probabilities retrieved from a z-table, and then the formula to convert it would be this down here. We'll be doing more specific examples. I think, actually, let me quickly check. We'll be doing more specific examples in the next study group. But basically, the z-score formula is down here. For any single point, like before we had 70, basically with the mean and standard deviation of that other normal distribution, we just take the point minus the mean divided it by its standard deviation to get the z-score for that point. And we'll talk about more why this is the case, this second equation is the case in future study groups, but if you have a sample, you can find the z-score for your sample. And you would just, almost the same, just instead of that, your standard deviation is divided by the square root of the number of things in your sample. I won't worry about that for now, but yeah. With your z-score, why we need to find a z-score, it's actually helpful for us to derive probabilities as well. So with these z-scores, we can actually find out cumulative probabilities. So if anyone's taken a stats class before, you might have seen that like wretched z-table, and there are other tables as well that we'll deal with in later study groups, but there's something called a z-table that you can actually look up, and let me clear this drawing first. With a given z-score, you can find the cumulative probability associated with it. So a use case, let's say, you know, we have this graph here, and we want to find the probability of, I guess, test scores being below 70, but it's going to be quite complicated with that like awful formula here. You have to do some sort of integrals and stuff. What we can do instead is convert this to a standard normal distribution and then just look up the z-score in a table. So in this case, after doing all of this transformation from 70, we get a z-score of 2. What we have in a z-score of 2, we can actually look up the cumulative probability. So how this works is z-scores can work up to 2 decimal places. And what you would look at here on the, I guess the y-axis, no, I guess the index column. The index column will tell you the first up to 1 decimal place, and then to get to your second decimal place is here. So for example, we had a z-score of 2.0. With a z-score of 2.0, 2.0 happens to be here, and then we have all of these numbers that get more specific, but here 2.00. The probability of a test score being lower than 70 will actually be 97%, 97.72%. If you have a z-score of like 1, it will be like 84%. What also makes sense is that if you have a z-score of 0, and a z-score of 0 actually means that, you know, your z is right in the middle, it's 50%, which makes sense because it's symmetric. And yeah, because of that, you also can have negative z-scores for any time that your score is to the left of the center of the bell curve. Questions so far? I will just preface this whole study group saying that this information is usually given over like 3 or 4 college lectures. So if this is a lot, no worries. I will say the main takeaways from this should really just be like what a PDF is and what information you can garner from it and like how to read it. I think that's like probably the most important thing from this study group. And then probably what a normal distribution is, like what characterizes normal distribution. You don't have to memorize or anything, but then if you see like a shape that kind of looks like a bell curve, you can sort of say, all right, this is probably a normal distribution. And then we will talk about like standardizing more in depth towards the end of the phase. So I know there's a lot of information there. If you're up to it, please like go through the material, but if not, just know how to read a PDF and like what you can garner from a PDF, as well as a little bit about the normal distribution. Cool. Any other questions? We are at the end of, yeah, I have no other slides after this. Awesome. So tomorrow we're going to be talking about, I think the central limit theorem is what I have planned for tomorrow. Yeah, central limit theorem and confidence intervals. It'll be a very similar, something like this. My study groups for topics 13 and 14 do kind of like go back and forth. So I have the slides already up if you want to like plan to go through more relevant material first. So I'll leave that to you. But yeah, if there are any other questions throughout the day, feel free to let me know. I do have a few more project reviews coming up. So I'll just get to your questions between those. But oh, one more thing that I realized. So with the grading, you're actually going to receive, I think, 2 emails because you submitted assignments on 2 different places, one for your GitHub repository and one for all those PDFs. So basically for the GitHub repository, you're going to get a complete or incomplete. Pretty much if you submitted your GitHub repository, it will be complete. But I will be only going through as I do your review. So you'll only get those grades after the review. And so with the GitHub repository, you get a complete, incomplete. And then with all the PDFs, that assignment that you put all the PDFs on, you'll get a 1 or a 0, depending on pass or not pass. So just look out for those. Cool, final questions. Going once, going twice. Awesome, I will see you all at tomorrow's study group or at your project review /101s. All right, bye everybody.
Yeah.
Thank you, bye.